Welcome to this talk. This talk is about how to build your own do-it-yourself Android kiosk. Now, this talk, things are covered in this talk. So if you've read the abstract, I was victim of hubris when I wrote this. Also, the fact that I wrote this abstract before I actually started working on the kiosk for my own projects. So we had 2 hours worth of material. I only cut it down to an hour, and we have 40 minutes. So let's get started. All right, so I'm going to be talking about your hardware options from single board computers to kind of kiosks frames that you can use to build your own kiosks. We're going to talk about Android user space kiosk mode, how to lock away the users from all the sensitive little screens. We're going to talk about a fair bit about low-level hardware interfaces, things like GPIO, PWM, I2C, little touching on SPI. I'm also going to touch quickly on microcontrollers and how you can use them to bridge the gap sometimes when you don't have like the exact kind of single board computer that you would want, or you want to use more standardized Android hardware. And I have like at the very end a couple of small kiosk applications, things that I've actually been working on, and I quite honestly are not complete. And I'll explain why in a second, so that's part of the story. And so things I did cut from the original abstract, so if you're here for that, I apologize in advance. We're not going to be talking about video recording or work log generation with AI. None of that's made it into the talk. And I'm also not going to go into weight scale integration or payment terminal integrations, because frankly, that would have literally exploded the talk into like 2-hour territory. All right, so who am I? My name is Etienne Caron. I'm part of the Google Developer Expert Network, or program, I should say. I don't put this slide there to brag. I really mostly put it there to say a big thank you to Google, who are sponsoring my trip here today. So a big shout out to them, and thank you for supporting the community. About me, well, I've had a long career, as you might guess from my gray hair. I've worked at all sorts of interesting places. I'll just keep it short. My last role officially, official paid job for an employer was with Shopify. I was a staff engineer there on their core Android team for their app. I left Shopify in 2020 to start my own little innovation lab called Canastruc. There's a funny story behind that name, but I can tell it to you after the talk in private if you're curious. All right, getting to the meat of the talk, hardware. So I've actually played around with 2 different types of platforms that I'm going to talk about today. There's the regular Raspberry Pi platform, which you probably know and love if you're into this room, because you're not here by accident, I'm guessing. And there's another very interesting one that I want to sort of showcase a tiny bit, called Odroid. So Odroid boards are made by a company called Hard Kernel. They're a Korean company. And so they have a really nice offering, I found, and as you'll see, they have some fun features to play around with, so I wanted to call them out. I have like a few charts on the kind of specs that you can expect from them. I think like the key part you need to sort of think about is if you've ever, like, who here are familiar with Raspberry Pis and have played around with them, right? Like I would say 80% of people here. So, performance for Pi 4 is actually sufficient to run the Android OS builds that we're going to show. Pi 5 obviously make things a lot more snappy. So if you look at an Odroid N2 and M2, they're kind of the same sort of level of performance. So we're talking like the difference between Pi 4 and Pi 5. I think the big thing that Odroid offers hardware-wise is that they seem to have a bit better support for NVMe drives and also eMMC cards, which are going to give you much better performance than an SD card. Price-wise, that's the kind of pricing you can expect. So that's, it's in the affordable range, I would like to say. So if we talk about the Pi, I'm going to talk about how to set up Lineage OS on it today. And so I wanted also to point out that there's some other interesting options. So Mteria is a very nice commercial solution, which I have not tried, but I've looked into it a fair bit. And they seem to be a really good contender if you're really looking to build more commercial space Raspberry Pi-based kiosks. And so, they come up with their own lineup of OS images. You're going to get security updates out of them. And they have a lot of nice customization options that you can apply to a fleet over the air and all of that. So they're really worth looking into if you sort of get out of the hobbyist space, which we're going to firmly be planted in today. You can try them out with 3 devices for free, etc. They have a paid tier. And this is why I actually didn't really dig into them all that much during the talk, is that it would have sort of sounded like a big sales pitch. So I didn't want to go there. But I do recommend you check them out. I'm personally quite sort of attracted to their offer. And they seem to be hobbyist friendly, unlike a lot of the other vendors in that space. If you want to talk about enterprise mobile managed kiosks, typically those companies sell the hardware, they ask thousands of dollars per tablet, and monthly costs are up there. All right, so Raspberry Pi, Freelands. So if you want to talk open source software, Lineage OS here, a specific build by Consta Kang. It's like one of the real only upkept modern Raspberry Pi builds out there from the community. So it's a non-commercial one that's worth mentioning. It's under Creative Commons. It's good for experimenting and prototyping. So installing this distro, what does it look like? It's very much like any Pi distro. It first involves flashing an SD card with the image you can get from this web page. You just need to pick the right image for your Pi 4 or Pi 5. They offer both. They used to have a Pi 3, but that's been discontinued. On Mac, I personally use something called Balena Etcher to make my own images. You could definitely use the Raspberry Pi Imager. So fairly standard stuff here. If you run into glitches with either software, one thing I ran into is try to uncompress your system images before using it. On Balena Etcher specifically, if you give it a zipped image, it's going to not work and not tell you why without any errors. So that can be a bit confusing. So a little side note there. And for applications that need more I/O performance, like I mentioned, do consider using NVMe. Full transparency, I have not had time to actually flash one and use it to give you the good news of how much more performant it is. But NVMe is fast. Install process for NVMe is why I put that slide up there. It's a bit more complicated, a bit more involved. When you use NVMe specifically for Pi, you're going to need to flash your Pi with the Pi image Linux, and then flash the NVMe from that Linux space to get to the point where you have a functioning kiosk. So it's a bit more work. So flash the SD card, takes a little bit. Once you're done, here I'm actually going to talk a tiny bit about what you're going to find on the image to give you a bit of a hint of how you can configure peripherals. So when you look at these images, you're going to find all the nice stuff, like the actual RAM disk images and all the things that are there to boot the system. The point of interest here is all the text files that you can find. So if you look a little bit at this listing, there's a config.txt and a config user.txt. And those files are pretty interesting. If you look at the highlighted section right there, that's the part that you might want to start playing around with. So if you are familiar with the difference between ARM and a regular PC, you might have heard that on a PC, right, you have a BIOS, so everybody I think is pretty much aware of that. And what the BIOS does is actually reports to the OS, hey, I have this hardware set up on this machine. ARM doesn't really have that. So you're responsible when you're building these images to tell the OS, oh, by the way, we have these things, and you sort of need to install these drivers, right? And so those drivers, those are device tree overlays. And so there's a folder in that specific distro, Lineage, where you have all the possible DTBOs, those drivers effectively, that represent things that you might have hooked up to the Pi that you kind of need to configure if you want to make sure that the OS is going to be aware of it. It doesn't only include peripherals, it also includes stuff that's actually on the device. So if you don't tell the OS that there's GPIO pins and I2C pins and all that good stuff, it will simply not be able to give you access to it because the drivers won't be loaded. All right, so more hardware notes. Raspberry Pi has an official touchscreen, if you're not aware. There's a lot of off-brand touchscreens as well, which are more affordable, frankly. But, even the Raspberry Pi one is not that pricey. So if you want the touchscreen, it's between 40 to 100 Canadian dollars, which in real money in euros is 25 to 65. So I have a couple of these screens. That's one I have. I've bought this quite a while ago. I've used it for my Pi 4 build here that I'm showing off a little bit. So this one has VESA mounts on the back. It has a fan. It has all sorts of nice things. It even has an external HDMI. If you want to connect other devices to it and switch the screen, you can do that. So, and those are fairly affordable. So that's it's worth looking into. All right. So once you've actually installed the Lineage OS, this is how it's going to boot. It's kind of fun. You're like, yay, it's working. Ignore the purple wire there. It's not actually connected to the Odroid. The Raspberry Pi 4 is in the case, and that's what's running that we're looking at. So here I have like a little bit of like, I wanted to show you what accessing pins in the user space looks like. So if you look at the menus I'm clicking on, when you're in Lineage, in the Raspberry Pi menu that you're going to have in the settings that's popped up there with the distro, you can tell it, I have these following peripherals connected to the Pi. So you can tell it I have a real-time clock, I have some sensors, I have some orientation sensors. The problem here is that your choices are kind of limited, which is a little bit of a bummer. We'll get to that in a minute. The other note about Lineage OS, which is why also you're going to realize I'm not going to talk that much about it today, is that it doesn't allow you to use it for commercial use. That Lineage OS build is strictly non-commercial. You can reach out the maintainer and ask about pricing, which I have honestly not, because I've sort of looked around. It's quite a nice OS, and I think depending on your needs, you might want to explore that vision. But like I talked about Mteria having a bit more commercial support. And on the flip side, there's the Odroid boards that I ended up like having a lot more fun with. So, you know, perceived perf, that's like sort of what we talked about already. So let's look at the Odroid, which drum roll I've been talking about a lot, so I kind of like that one. So Odroid, they're the ones recommending using the Balena etcher to flash your images. Side note about the zipped images, don't forget if you get stuck. I ran most of my own tests with an SD card, but they have like an eMMC that you can buy that's pretty cheap that improves the performance that you can play around with. A little video there is showing me playing around with one of those. Definitely something you might want to look into. So once you flashed your image and you run the install the first time, the thing is that on Odroid, when you look at the partition first, you're going to realize there's not much there. And that's because the way they've built their own distro is once, you know, it's a recovery type image. So you need to put the disk in there, run once for it to go through an Android update process where it's going to do the partitions and actually install the OS on the device. So if you look after having run it once and you want to look at what are the initialization files and maybe play with those device overlays I've talked about earlier, in this case, they're not in config.txts, they're in these INI files that you might want to look into. Here I have a little, just showing a little bit that the partitions are actually getting installed after the first run. All right, so once you've done that and you have Odroid running, the thing I want to point out is that you get a special little menu called the Odroid settings. If you open that up, you're going to have like this DTB overlay menu choice that you can use. What is that? Well, if you actually don't want to swap out your cards and start playing with the INI files, they have conveniently put this little dialog there so you can just manually edit that straight from the OS, which is kind of nice, but also kind of dangerous if you mess up. You can sort of break the whole OS. So yeah, typically you only play with this when you actually want to remove certain features. Pinouts are different. We're going to talk about how that works in a second, but you might want to have a pinout that's more similar to Raspberry Pi, and to achieve that, that's where you're going to play around with the settings. All right, so I'm taking, time-wise, I'm a bit worried, but we'll get there. All right, so working with aluminum extrusion. So this is how I've played around with building my own kiosk, and I think it's like a really good way to get like something sort of, you know, minimum viable product ready. So aluminum extrusions, what are they? As pictured here, you can see there's like there are these aluminum tubes, and they have grooves where you can install different hardwares to try to mount them together in something like this setup right here. So this is a photography rig. It's built to be able to position the camera at different angles. You can see that there's a linear actuator at the back. There's like a little turntable at the bottom. They have like a backsplash sheet and some lighting. And all of that is controlled in this case by a microcontroller that's at the bottom of that specific rig. So when I talk about kiosks, sometimes people ask me, what do you have in mind? This is my fancy way of looking at kiosks. Like, it's the kind of thing that you can build if you want effectively a dedicated device, right? So hardware-wise, what can you do with aluminum extrusion? So pretty much sky's the limit. The way they're built is they're really built to accept standard connectors and fasteners, and you can buy all sorts of those online. For the extrusions themselves, it's usually much cheaper to buy long extrusions at like a hardware store or a other provider and cut them yourself. which is what I've done here in the picture. So that's not my miter saw, but a good miter saw will do a really great job at cutting these things. One side note is you do need to buy the right blades, not to hurt yourself. Safety is important. And the other thing too is that you really need to secure pieces if you're going to work with with a miter saw, because they're kind of a crude-ish tool to cut aluminum extrusions, but they do a good job if you take security precautions. If you're a bit fancier and you kind of want to have like the perfect rig, you can use aluminum extrusion to build your own aluminum extrusion build cutter. This is like a router with like the right little equipment and a control. So I have a URL down there that explains how to build your own from Hackaday. So if you're a bit obsessive about this kind of stuff, which a little bit more than me, but I'm kind of thinking of building one of these myself, that's something to check out. All right, so you can buy some nice hardware off the shelf to assemble frames together. This on the left you have a 3-way corner, on the right you have a 2-way corner to assemble the shapes. The way these things work is that you have these little worm screws that you can use to tighten them in place and make the frame really solid. Those tend to be a little bit pricey, a bit rich for my sort of taste. So what I've been doing is I've actually sort of used that budget to buy myself a 3D printer, and I use more standardized T-nut inserts with 3D printed parts that way, right here. So those are, the little metal pieces here are really cheap to buy. And what's nice with the 3D printer as well, it's worth mentioning, that you can start building all sorts of little bits and bobs that tend to add up when you do a build. Like these things, they might look like they cost, well, they actually cost like 2 cents of plastic to print, but if you buy them, they're going to be like almost $1 online each, which is a bit rich again. So you can also do a bit more fancy parts with 3D printers. So more structural parts like this or like these, 3-way corners, these are really awesome. Now you might be thinking, Etienne, don't 3D printed parts, like break whenever you apply a little bit of force? And so the trick with these is you want to print them at an angle like this. So when you print them like this, what happens is that all the layer lines are against the planes of force and not with them. So they're not, I'm probably not saying that right, but effectively what it means is that the part is much more solid, and you're not going to break into layer lines when you're going to try to apply force. So I tried as I might this setup here. I never managed to break one of my corners, like actually like literally trying to break them apart, nothing budges. So they're a really good construction part, and they are really much cheaper than the metal parts I just showed you to print. Now, other stuff that you can do with a 3D printer, I'm showing a couple photos here of some clips I've used to hold phones when I built kiosk prototypes. So those are kind of neat. The idea, I've just put this stuff here to give you an idea that the sky's the limit once you have a 3D printer and you start using aluminum extrusions. Another thing you can do when you're working with this stuff is to drill and tap holes straight into the armature. So here I'm using an M5 tap. So usually you buy these kits, you drill a hole, and then by using the tap you can fillet the actual hole in a way that you can use standardized M5 screws to put everything together. So if you have, some people build computer cases out of this. So they put the tubes in the right spots. They really measure everything nice and tight, and they start putting down the screws in the different places with the right size holes. And you can sort of, fix computer boards to this. Sky's the limit, really. Once you start messing around with this stuff, it's kind of really Lego for tinkerers. All right. So all that said, the goal for my first kiosk was to add like a VESA-compatible mount to my frames. And VESA, just a note on VESA is just a fancy way, if you're not aware, of saying that you have standardized sizes and gaps between the screws. So the little metal inserts that you see there, if you have a VESA-compatible mount and you put it on your frame, you can bolt any type of screens basically on your frame, be it the Raspberry Pi or even standardized TVs have these. So you can do a lot of stuff. And then you can even start playing around with monitor mounts and sort of making Frankenstein constructions. So that's kind of cool. All right, enough about like physical hardware. I'm gonna fly through the Android kiosk mode stuff. I know, well, how to put it gently, like they do a really good job on the Google sites to describe how this works, and it's kind of boring. But effectively, the goal here is just to say my app is like the app in charge. And unlike, I don't know, like the usual anecdote is you're in a plane, it's an Android tablet showing you the movie, and you find the menu to slide up and get into the settings. Goal here is not to allow for that, right? And so the way to do this is there's like the canonical way. There's a lot of documentation. I really suggest you just take screenshots of the URLs, but I'll give you like the TLDR is that to manage these kind of kiosks and really lock everything down safely, what you want to do, first off, is you want to hand off the rights to your application. I have this right here. All right. So this is the ADB command that you can use if your device has not been provisioned as belonging to someone, right? So what I mean by that is when you use your phone and you start it up, usually you sign in as a user, right? So in this case, the scenario is you don't sign in as a user, there's no user of the device, and what you want to do is take your app and make it effectively the user of the device. And by using this command, you can do that. And once you do that, what happens is that you register your own admin receiver to be like the person, the process in charge or the receiver in charge of handling demands to lock the screen and sort of take over. So when you run this command, you're effectively granting that right to your app. And once you've done that, what you want to be doing is start calling these functions. So this allows you, once you've gotten that right, to call start and stop lock task right there. What does lock task do? Well, it sort of says nobody's allowed to kill me. It also makes your app responsible for saying things like, I don't want the users to look at notifications, to get access to settings, to slide anything around, to nav back, to go to home, I'm home. So once you've executed the start lock task, then your app is effectively in kiosk mode, really, at the end of the day. And the fun part is you can stop that if you want, during development to sort of turn that on and off and sort of test it. That's the key gist part of this section. And if you've sort of taken the URLs down, you're going to find like a lot more information about interesting things and important things like how to do this work at scale. So in this documentation, you can also find ways of setting up your own enterprise management, mobile management service. You can make your own. There's even pages in there how to actually register as an official one. There's certain things that they don't allow you to do anymore. They don't allow registration for device policy controllers. So that's not something you can do, but it's not something you care about. Like at the end of the day, if you wanted to write your own fleet management software, all the links are in there. You can actually do that. That's possible. It's not something I necessarily recommend. It seems like I've played around with it, and it's like quite the rabbit hole. All right, so let's get into hardware. We're 20 minutes in. We're sort of good. I'm going to try to get to... This is what I think is the meat of the talk. Hopefully your feedback will tell me if I'm right. All right, so GPIO pins. So who here's actually just a sense of it? Like if I talk about GPIOs and I2Cs and SPIs, who here has any idea what this means, what I'm talking about? Okay, so we got a good half of the crowd. I will take time to explain it a little bit for the rest of you, right? Just to be polite. So access, like GPIO pins, those are like physically the pins that you find on a Raspberry Pi. A lot of them, like they all have different roles. And the GPIO pin is like the simplest one. It's the one that allows you to turn on and off a signal. So if you want to turn on an LED, you're going to effectively connect it to a GPIO pin with a little resistor. We're going to do that in a minute. And turn that on or off. If you want to read one single button's state, you can do that with a GPIO pin and find out if the circuit is open or closed, right? You have another category of pins on these boards that are called PWM pins. So they're pulse width modulation pins. They allow you to generate a specific electric signal. We'll see in a moment what that's for. And you have more complex pins, and those are the I2C and the SPI pins, and you even have something called a UART pin. So if that's all sorts of alphabet soup to you, the way to sum it up is they're all buses. They're all a way of connecting peripherals one next to another and addressing them and talking to them and getting them to do fancy things. So the PC equivalent would be having a card in a PCI slot. That's kind of like the idea, except here you only have 2 or 3 or 4 pins depending on which we're talking about, to communicate over that bus, right? So it allows you to connect a lot of devices on fairly limited amount of connectors. All right, so last note here is that the Odroid and Raspberry Pis have similar but not exactly identical pinouts. On the Lineage OS install, I've talked about the device tree overlays. So here I'm quickly just showing on the Linux command line how you can find out which pins are activated, which services are there, and if everything has been configured properly. You want to play around with these commands if you suspect that somehow I2C is not working, or it's not there, or that the GPIO pins are not working. And on the Lineage OS, you might want to do that when you want to access sensors in Android user space, and for some reason it's not working. But so Lineage has all these little packages installed that you can use. So they have, oops, I just ran out of the, oops, give me a second. We're back. So yeah, you have the GPIO detect and I2C detect commands and all that provided by the Toybox sort of multi-user tool that they set up in the distro. To keep things short, they allow you to, at the Linux command line, find out what's actually recognized by the OS. What's kind of sad here, and I've touched on this, is that in Lineage space, you can't access the GPIO pins and the I2C and all that directly, so you can't really have fun with them, as we want to do today. The fun bit is that the Odroid folks, there we go, have found a way to make that accessible to Android user space. They've effectively resurrected Android Things from the dead, which I was, to my pleasant surprise, I was a big fan of Android Things. And so what they've done is that they took, Android Things has one portion that's open source, which is effectively all the interfaces and a lot of the drivers for different peripherals that were written by external people than Google. All of these are still online and available on the internet. And so what Odroid did, and the story is at this link right there, one of their engineers decided to effectively recode a library.so that provides the same services almost that Android Things used to. And so all of a sudden you reinstall the Android Things packages and they actually work on these boards and they allow you to access GPIOs, I2Cs, and all that good stuff. There's a lot of examples on their wiki. You can download the original source code here, so I'll leave it up a second if you're like curious and want to follow along at home with one of these. And once you've done that, you can start like playing around, and their examples are really good. So I'm going to go over a couple of their examples to get warmed up a little bit. And so, well, how am I on time? Yeah, okay, because my timer reset, but I'm good. Actually, I know I have like 15, 17 minutes, right? All right. So right here, LED time. So that's always the simplest example. This is how you hook it up, which the right pins and all that. The way I've done that at home is I've used a Raspberry Pi GPIO extension board. So that allows you to put a breadboard right next to your Odroid and just like start experimenting and doing all sorts of fun stuff. So that's what allows you to like effectively connect these LEDs with a little less trouble. So this is like the sample code on how to connect an LED. So you see it on the left. Very simple, turn on and off, open the LED itself. The thing that's maybe more worth of note on the right is you're seeing the Android Things interface for controlling a GPIO pin. But not only that, you actually see the peripheral manager, sorry. The peripheral manager on Android Things is what allows you to reach out to all the GPIOs, yes, and PWMs and I2Cs and all these pins at a low level. So that's what all the drivers that you're going to find in various open source projects are built on top of. It's actually fairly easy to write your own Android Things driver, is worth mentioning. So in the case of the LED here, yeah, I usually don't go over this kind of code in detail. I don't think it's really super interesting. The key note here is to see that, once you've used the peripheral manager to map out all the GPIOs that are available, like as this example does, you can play around with the switch and it'll actually like turn the GPIO pin on and off, right? Pretty straightforward. A bit more interesting of an example, again from Odroid, is how to work with a rotary encoder and a servo motor. So let's dig into this one a little bit more in detail. I think it's worth it. All right, I'm just want to be able to highlight code slides here a little bit. So let's see. Yeah, so when you write your own project, but in the sample you're going to find like the key items in the Gradle.build file are, oh come on, sorry, technical problems here. All right, so the key items are here. So the implementation details. So you're going to have, yes, the Android things distro and a driver for the PWM servo right there, and hard kernel have their own Android things drivers that they've published, and that they have repos available for that. And once you install all these dependencies, what it allows you to do, it gives you access to this servo class right there. And thanks to that, you can access the servo without necessarily knowing all the technical details behind one. And by giving it a few parameters, like what are we'll talk about these features in a sec, but by giving that a few parameters, you get at the end of the day a servo class that you just call an angle into, and it's going to position the servo to that angle. So I have a few slides on how this works under the hood. So you can see the servo code right there. Like the main thing I want people to notice is that it's built on top of this right here, PWM. And that PWM device is something that Android Things is provided for us at a lower level. So if you dig another level deeper, you can see that the PWM interface right there, has like very few actual methods, right? You have a set enabled to turn it on and off. You have a close to close it when you're done. And the two key things here are you have a set the PWM duty cycle and a set PWM frequency. So what does that actually mean? So let's look at how that works. Like what's a PWM if you've never played around with this? So PWM stands for this. So it's a way of communicating to something that's connected to it, like effectively a power level, right? Like think of it as a gradient. And the way you do that is you have a certain frequency that the thing you've connected to that PWM port expects. So let's say it's like 20 hertz or something. And that means that every 20 times per second, it expects like a pulse. And you have a duty cycle for that pulse. So you can see it in the graph here. By controlling how long you turn on the signal every 20th of a second, you should have communicate to the device, in this case our little motor, how much it should turn one way or the other. And that's all there is to it. And so by calling the other two methods I showed earlier, you can say the frequency and tell it the duty cycle, and that's what you're communicating effectively to the servo. Now, servos here, a little bit more information on what they are. I would just recommend taking that link down if you don't know what this is and you're curious. But we can see a hobby servo up right, and they're just like little motors, right, connected to a series of batteries. Very simple stuff. And they are controlled, as you might guess, with a PWM signal. And right here, we could see exactly how that works. So if your servo is at the center position, it's expecting a certain signal. If it's like all the way right, all the way left, it's expecting another signal. So that's what we're trying to communicate to the part. All right, so again, Odroid have like these nice little diagrams on how to hook this up and try it for yourself. As you'll notice, I'm skipping over the part where how to read from the actual rotary dial, because that's a bit of a rabbit hole on its own. But what I wanted to really show folks here is the actual experiment going on to get like a feel for what exactly all this is and how it works. So this is my version of this. I found a nice little knob to go with the rotary encoder. And you can see I have like an oscilloscope hooked up to sort of give you all an impression of how that actually works. So if you pay attention at the bottom right, you can see the servo actually shifting from right to left. And it's kind of subtle here, but you do see on this oscilloscope the part of the duty cycle I just talked about, like changing in time. So the longer it's on, the more the servo turns one way or the other, if it's shorter. You can't hear this because I don't think I've hooked up sound, but one thing you'll note if you play around with servos is that if the values in the code are not correct and you're going outside of the bounds, whenever you're sort of going over the kind of duty cycle it accepts, you're going to start hearing it click and sort of struggle against the limit of the actual mechanical little thing. So yeah, that's something, if you experiment with it, pay attention to that, not to burn out anything. That's just safety measure. And so here it's a bit more clear how long the duty cycle is affected while we play around with this. All right, so having seen all that, I hope that it gives you an idea of what PWM means if you haven't played with these things. So yeah, going on to the next part. Yeah, that was code that showed how you update the cycle. One thing you'll note in those examples is they have very fancy formulas on how to calculate, how to map an angle to a PWM cycle. But once you know what it is, you can figure out the math later. It's not that interesting. All right, so knowing about PWM, these are the pinouts that are actually used for a PWM. So there's dedicated pins for that. Just looking at time, we're sort of okay. All right, one thing I did want to touch during the talk, if you follow my examples, you're going to hit a snag. And the snag is JCenter. Who here knows about JCenter? Yay, JCenter, thank you. Well, I shouldn't be that sarcastic. They decided to not provide a fee service anymore, fair. Problem is, Android Things was around before JCenter went away. So while Android Things, the library, is hosted by Google, thank you, Google, the actual user-contributed drivers that are managed by Google have not been pointed to a new repo and not been published. So if you want to use these drivers, as I did, you're going to have to build them yourself. It's not a big deal, but I did want to point out how to do that and how, I want everybody here to actually experiment like I did, because it's a lot of fun, frankly, and it's not that complicated as long as you fix this problem. Right, so building your own local artifacts. Who here is familiar with just running your own local artifacts and publishing them locally, right? So it's not that complicated. Effectively, you just need to know that there's a Maven command that allows you to publish to local. And all this stuff I'm sort of going to publish on a GitHub a bit later. So I'm going to really jet over this because we don't have the time. But these are very limited, small changes I needed to do to the Android contributed drivers to be able to publish them locally. You need to take out all the JCenter references and make sure that Maven local is enabled. And that's effectively it. And then you can start publishing your own locally and get access to those drivers without having to go through JCenter. And that here is the end command that you need to run effectively, right? Nothing, no witchcraft involved, but good to know. All right. I have enough time to touch on I2C. Yeah, I'm kind of short. I think I2C is an important part of this talk, so I do want people to be aware how it works. But why would you need it, right? So for any advanced kiosk, I2C is going to allow you to do more fancy things. I just showed you how you can control one motor, right? That's fun. But you also saw that there's 3, 4 PWM pins on a Raspberry Pi. And you might wonder, oh, what happens when I have bigger motors? Can I drive them through that? And the answer is no, right? Anything that requires a big voltage will require separate electronics not to fry out your little computer there, right? And so at that point, you need to start thinking about add-on boards. And add-on boards usually communicate with the Raspberry Pi or the Odroid, or for that matter, any microcontroller you hook up to them through a hat like this. If you've been to one of my previous talks, I've actually used these hats and talked about them here before. But so these are I2C enabled. You can stack 64 of them on your kiosk if you wanted to, and they allow you to control both little hobby servos like these, or bigger motors. So they allow you, and because they take their own independent power supply as well. So then you can get up to fancy shenanigans like that camera rig I just showed if you start using these kind of peripherals. And that requires you to use I2C, which is why we're actually talking about it. Do note down pinout.xyz. That's actually a really great little site I found to learn a lot about these things. Although I'm here talking to you about all this, I'm far from an expert with this stuff. I learned a lot of it from this website and the other resources I've just shown you pretty much on the fly. Anyway, so here you can see the different pins involved in controlling an I2C signal. Yeah, and that's the ones we're going to use. Now, not to be too low level and find a way of quickly getting up to speed, I've actually used the good old rainbow hat. Who here knows what the rainbow hat is? Okay, not a whole lot of people. They used to give those away when they were promoting Android things. And so an English company called Pimoroni was making it. They're sadly discontinued, but if you want equivalent toys, they still have them for Raspberry Pi. So if you go look up Pimoroni, they have like a lot of things like that one that you could purchase to try and test out all the different little signals I'm talking about here today. The reason those hats are interesting is that they have an SPI device or two, they have I2C devices on them, they have GPI open features, and all that on one hat. So if you just want to test out that you've got these things working on your boards and that everything is like tip-top shape and that you can use other types of I2C signals and devices, these are like pretty good to start with. Thing I did run into here is that the pinouts are slightly different between these two boards. So they have a bit less GPIO pins on Odroid that they're using for different purposes. So that actually required me to tweak the rainbow hat driver that's available, part of the contrib drivers. Long story short, that orange block right there is the one that's in contention. Happily enough, I2C pins are the same, SPI pins are the same, so the sample kind of worked without too much trouble. But to not have problems, I did have to remap a few of these, and I actually also had to make the rainbow hat aware that there are more devices out there now that can support it. But nothing terrible, and I'll make this code available on my GitHub as well. That was like all the changes I needed to do, pretty straightforward. At the end of the process, you publish your own driver locally again, and then you can start playing around with the code I'm going to show here. So I'm going to fly over it a little bit, but you know, if we focus on like the core of it, the way that these things work, this is like sample code for 3 different things. For a straight up turning on and off an LED, they have a nice LED strip that can do a rainbow colored thing, which is why it's called the rainbow hat, that you can use as well. And that's an SPI device, and there's an I2C example there at the bottom where they have a little LED display, segmented display that talks, that is addressable via I2C. And so I have like, I'm going to go really quickly over this because we're almost out of time, but like the core of it, and I'll make the slides available on the GitHub as well, by the way, so that you can actually look into this, all that. But the core of what I'm showing here is effectively that it's always the same pattern. You're in user space, you call your contributed drivers, and eventually they end up calling the lower level Android things libraries, and those just play around a little bit more directly with the bits that are needed and the bytes that are needed to be pushed down the pipe for the different components to turn on and off. So here that code was just like turning on an LED, a little red LED. Sadly, the blue and the green LEDs are not addressable from Odroid. You have to scratch those off. Then there's code that shows off how to use the SPI. And again, same kind of thing. You end up going through different layers of like a contributed driver that makes things easy to work with that specific rainbow strip, all the way down to code that talks I2C and communicates directly with it, and that does fun stuff like turn on the LEDs. In this case with SPI, I think I just said I2C, not my mistake. Then the I2C example is very similar. The driver here takes the text, turns it into segmented displays, eventually trickles all the way down to the lower layer, talks directly to the device, and we get an incrementing counter that I don't have animated here, but this right here is a /3/, and the code in the sample iterates over that every second. Now, things I'm going to touch on really quickly, and I'm not going over Elaine's talk yet, so I'm good. But I think they're kind of important if you're going to experiment with this stuff. So, logic analyzers. The thing is, you saw my fancy oscilloscope. That was a cheap one, and it cost like about 800 bucks. That's not cheap, right? So if you want to experiment with this stuff, you might want to do it on a cheaper level. Logic analyzers, typically, if you buy like a Pro one, that's $1,000 to $1,500 extra on top of the oscilloscope. Sometimes you can buy logic analyzer modules for the oscilloscope. Those are like $1,500. So it's kind of like a pricey hobby to get into, right? This thing is 25 bucks. It's like a knockoff. It's not even mini USB. It's like it's mini USB, not micro USB. So it's really an old piece of tech. But it works fine for all the hobby stuff and all your needs for debugging I2C and SPI and all of that. How does it work? You hook it up. You sort of get this open source software called PulseWave right there. I forgot to put the URL to that, but PulseWave. And if you look up like cheap logic analyzer, you'll find all the docs online, I swear. And so once you've set those up, you can actually find out what's going on at the pin level. So it's going to tell you that's the system clock. That's where we sort of synchronize the passing of the data around, and that's the data line, and you can actually see the signals being passed around. And what's really neat about these logic analyzers is that they allow you to do something fancy, which is effectively look at the data that's going over the line. So this is an analysis I ran while the counter was incrementing. And if you sort of squint, you can see that those blue rows of numbers are actually the binary data of the segments changing in time and being told, telling the device how to run it. So if those are kind of vital, these kind of little pieces of things, because if you want to debug stuff with electronics, it gets frustrating really quickly. All right, last note, if you don't have these boards, all this pinout, all this stuff is too much, too complicated, or that you simply don't have an Odroid device and you kind of want to work with these ideas, you can use a microcontroller instead of using Raspberry Pi pinouts. Microcontrollers like these allow you to control parts like that one, which are very time sensitive. You can't, you sometimes even need them with a Raspberry Pi because Raspberry Pis are running Linux. Linux are not a real-time OS. And so if you want to do like a PWM signal off of code that you wrote, it's impossible because you will never hit those timings. As soon as something interrupts, you're going to get like a messed up signal. So you need kind of microcontrollers for those kind of scenarios, and the scenarios where you just want to connect, like here, a phone to a microcontroller and eventually a hat to control like little engines. So here I'm just showing off the fact that these are addressable via COM port over USB. So you effectively can do all the examples I've talked about today with I2C and LED and all this nice electronic stuff using a microcontroller connected to a regular phone or tablet. And the only thing you're going to need to learn is a bit of C, which would have sounded like a nightmare 5 years ago. But I hear there's these really nice things called like AI assistants nowadays that can help you code this kind of stuff, like while you sleep. All right. So on the Android side of that, last note, there's a library called USB Android Serial Android. Not going to go over the code samples for that. Jumping over that. Almost done. Yeah, and I'm just going to touch on applications and close off this talk. And so I've actually been using this kiosk stuff for my company I'm part owner of. So we're like a junk collection agency. And one of our services is we empty out people's apartments, for successions or whenever, say a more concrete case, an office wants to get emptied out. And one of the things that happens is when they empty out these offices, very often we get a call, a week's notice. Imagine this space, multiplied it by 4. We emptied out a whole floor, almost brand new furniture, and ironically enough, a mobile development company in Montreal, like a big agency. No relation, even though I'm into mobile and stuff. And then they called us, we emptied all that out, and we threw away like 80% of it. And it's all brand new IKEA furniture, which is like a damn shame. And to avoid that kind of scenario ever repeating again as much as possible, what we needed to do was to create this sort of system where we could inventory on the fly all these things very quickly and even allow our users, our customers, to create that inventory. And so, long story short, the kiosk kicks in once we have this whole inventory system and we're down to the warehouse. Our problem at this point is we need something that the employees in the warehouse can use to check out the devices, scan QR codes, and just ship it out the door and make a bill for the customer that's getting this, or just like tracking the inventory if we're giving it to Goodwill and things like that. So that's like effectively the kind of uses you can get out of a kiosk. And I know like it's a very pointed case, but that's like a case. At this point, I have a slide that I forgot to put a photo apparently into. Another case that's kind of useful for kiosks is inventory management for like a bigger collection. So an example I like to give is record collections. At home we have, alongside the business, sometimes we get collectibles. So we have like now a collection of 5,000 records. I'm not even kidding. It's like it takes up a whole room. The problem with this is you need to inventory it, right? And to inventory it, what better than an actual over-the-shoulder camera scanner that can look at the records, sort of reposition the picture, identify them, find out automatically if they're worth something, and then even better, actually generate the product description automatically for you as well. So we've been playing around with these ideas, and we have all that code working. And frankly, the last leg of it is to make it really useful. We want to have that you know, you don't want to hold your phone and film all this stuff. You just want to have something on a tripod effectively that looks at what you're doing and gives you a full report and actually generates these product descriptions on the fly for you. So, you know, we've found a few use cases that are pretty magical, and you know, that's about it for me today. I just hope that you find your own magical use cases to work with, and thank you very much. Now, I'm just going to put up a last slide here. That's just to say, if you want to contact me, so I'm in business on my own now. If kiosks interest you and you feel like, I want to play around with this stuff, but I want some help, I'm not actually here selling you my services right away. I'm really literally saying, as part of the GDE, if you're interested in this stuff and you want to talk for a couple hours with me for free, call me up, ask me all the questions you want. You can find my LinkedIn here. You're going to find a GitHub that's going to be updated a bit later as I finish up all the actual concrete work on this. And I hope to hear from you at some point in the future. Thank you very much again.